Hey guys, Miss Marusik here, and in this video we're going to do a refresher of all things compound stoichiometry that we learned about in pre-P chemistry. And now this chart might look familiar to some of you. It's just kind of a conversion chart that we can use to work our way back and forth between different units. So for example, if I want to work between formula units for ionic compounds or molecules for covalent compounds and moles, I would use Avogadro's number. Or if I want to work my way between moles and mass, I would use molar mass of a substance. Now, just as a reminder, anytime I'm doing one of those two conversions, I would always want to use one with moles because of the definitions of those two conversions. Avogadro's number is how many particles are in 1 mole, or molar mass is how many grams are in 1 mole of a substance. But let's say my conversion that I'm trying to do is not converting between the same substance all the way through the problem. Like I'm not working with water the whole conversion that I'm doing. I might need to do something a little bit extra. So for example, let's say I was trying to get between molecules of water and the number of hydrogen atoms inside of it. I might need to set up what's called a particle ratio, where I can say for every 1 molecule of water, there are 2 molecules of hydrogen inside of it. Or maybe if I was trying to do a mass ratio, where I was trying to get between the grams of water and the grams of hydrogen inside of it, I could set up a mass ratio. For every 18.02 grams of water, the molar mass, there are 2.02 of those grams coming from hydrogen. So I could kind of set up those extra pieces depending on what kind of conversion I was trying to do. Now there's 3 things that I want to kind of call our attention to that we want to make sure that we're being very careful about as we're working these problems. First and foremost is show your work. I can't begin to stress how important this is on the AP test. You can have the totally right answer there, and if you have not shown your work or the grader can't follow the work that you've done, you won't get credit for that problem. So it's very important to show work clearly, and most of the time if we can use dimensional analysis for a problem, then that's what we should be doing. I've seen people try to use all kinds of crazy cross-multiplying fractions and all kinds of crazy proportions to try and do these, and it's just a hot mess and impossible to follow that work. So dimensional analysis is always the best bet when you're trying to do dimensional analysis. Also, don't be lazy on your units. I can't tell you the number of mistakes I've seen people make where they're not showing those units and they don't recognize that they're in the compound and trying to get to the element inside of it, or they use Avogadro's number when they're trying to go between grams and moles because they're not recognizing what units they're working with. Last but kind of least in this case is consider significant figures. Significant figures are a really minor part of the AP test. To be honest, only 1 point out of all the points on the AP test come from significant figures themselves, but it is something we want to be cautious of. The good news for us is that with dimensional analysis, significant figures are super easy because however many significant figures the original number has is how many we show in our answer. Any constants or conversions that we use in our setup don't apply to significant figures. So like I said, pretty easy to do significant figures when you're using dimensional analysis. One other thing I want to kind of talk about are that there's going to be different ways that you can do the same problem. And again, as long as you're showing your work, you could do this problem several different methods, okay? This is a great example of that. I have a 125 gram sample of Beryl, which happens to be a substance that's inside of emeralds. And I want to get to how many grams of beryllium are in the sample. So we can see we're trying to work back and forth between this compound here and grams of an element that are inside of it. So I'm going to need to do something a little bit extra than just going between grams and moles and particles. I'm going to need to set up some sort of ratio between the compound and the element inside of it. And there's a couple different ways to approach that. Method 1 here is using what's called a mole ratio, where I can set up a ratio between 1 mole of my overall compound versus the number of moles of element that are inside of it. So you can see here they started off with 125 grams of the Beryl. to grams to mole conversion. And then here's where that mole ratio comes into play. 1 mole of the compound for every 3 moles of beryllium inside of it. And then they just took moles back into grams of the beryllium to get their answer. By the way, this is one way you could show your dimensional analysis. I'm going to show you 2 other ways. I know a lot of you are used to seeing this kind of, I don't know, T-shaped kind of setup. That's something that's pretty common amongst teachers to show that T-shaped setup. I actually like to use this parentheses setup here just because I plug it into the calculator exactly that format. So that's just kind of a personal preference. But all 3 of these formats show exactly the same work. So don't get freaked out if you're using one or the other. Also, I want to point out, like, instead of writing this whole compound every time, if you're in terms of the compound and you want to kind of shorthand your work a little bit, you could use CPD as an abbreviation for compound. So that way you can make sure you address where you transition between the compound and the element within. Some other options you also have to solve this particular problem is that you could have set up what's called a percent composition. Percent composition is where you have the mass of the element inside of the compound over the total molar mass of that substance. So for example, here out of the Beryl compound, there were 3 berylliums inside of it. So 3 times 9.01, the molar mass of beryllium. Grams came from beryllium out of the total of the 537.50. I then multiplied by 100 to get into a percent, and then I could apply that percentage to the original 125 grams. Now, obviously, applying a percentage, you have to change it back into a fraction, and so then that gets the answer that we saw up here of 6.29. Method 3, which is actually my favorite of these 3, is using something called a mass ratio. I talked a little bit about this earlier. Once I see I'm going between the mass of a compound to the mass of an element inside of it, I set up a ratio of the mass, the molar mass of the whole compound versus the molar mass of the element inside of it, addressing how many of that element were in there. Now, I want to kind of show you something about this. If you notice, this piece right here is exactly the same setup piece as we saw in the percent composition. Also, the math that these steps are doing is the exact same math you did in this first example here. I have the 537.50 on bottom divided by that number, and then the 3 times the 9.01 on top. So the reason why all 3 of these methods get the same answer is because all 3 of these methods are doing the exact same math. Okay, it's just a different way to think through those setups. So this really is a matter of kind of take your pick on what you feel most comfortable with. As long as you're making valid conversions, you should be getting the same answer no matter how you're setting it up. You just want to be very careful of those units and when you're dealing with the compound versus the element inside of it. So let's go through and do kind of a set of examples together on the next page. This is using something called Freon 12, which is a chlorofluorocarbon. It has chlorine in it, the Cl2, has the fluorine in it, the F2, and carbon at the front of it. So chlorofluorocarbons have been found more recently to be bad for the atmosphere. It breaks down ozone, which is not good. And so they've kind of replaced traditional Freon with some new formats over the last couple of years. Really old air conditioners still use Freon, but the new ones do not. So we're going to do these calculations for the Freon, the CCl2F2. And the first thing it asks us to do is to find the molar mass of CCl2F2. So this is where I would want to bust out my periodic table. Let me grab mine here. And I'm going to go find these elements on here and go see what their atomic masses are. So for carbon, I have 12.01. And there's only one of that. For the chlorine, I see it has an atomic mass of 35.45. And there's 2 of those. And then for the fluorine, we have a mass of 19. And there are also 2 of those. So then what we would do is, of course, we would add up these masses to get our overall molar mass. Now I'm showing way more work here than what I would probably typically show for a molar mass. Usually if you're doing some sort of dimensional analysis problem, they may even give you the molar mass within the context of the problem. But if they don't, you are allowed to just calculate it on your calculator and plug it into your math. You don't have to necessarily show all this work for molar mass unless specifically requested to. This gets a number of 120.91, and the unit for molar mass is grams per mole. Now, I will warn you, sometimes on the AP test, instead of doing per units where they show grams divided by moles, instead they will write this unit as grams times MOL raised to the -1. Remember, anything raised to a negative exponent is the same thing as dividing by that variable. So grams times moles to the -1 is the same thing as showing grams per mole. I just want you to be kind of familiar with that setup just in case you see it. So there's our molar mass for that particular question. Part of the other reason why I showed this much work here is because I knew I needed some of these numbers for the next part. So on the next one, it says calculate the percent composition for each element found in CCl2F2. So we're calculating a percent composition where we want the part of the mass that came from that element over the total molar mass and then converted that fraction into a percentage. So for example, let's say I was trying to do the percent of carbon here, okay? In the total molar mass, only one carbon existed, so I just do the 12.01 grams over my total molar mass of 120.91. And you can either write CCl2, F2, or you can put like of the compound CPD. This would obviously get us a fraction. So then to get into percent, I would multiply it by 100. This gets us a percent of 9.93%. By the way, in something like this where I didn't have any kind of starting number given to me in my problem, a good rule of thumb is to show 2 places past the decimal if you're ever in doubt. Here with percentages, I usually do 2 places past the decimal. On these next problems where we have a given number, we'll talk about sig figs when we get there. But on something like this, this would probably not be a question that AP would be grading for significant figures. All right, so then next substance in there was the chlorine. So to calculate the percent of chlorine, I have to be careful because there were 2 chlorines in there. So I need to make sure that I do the 35.45 times 2 for the grams of chlorine inside of the total of 120.91 grams of the whole compound. And of course, times by 100 to get into percent. This gets an answer of 58.64%. And then last but not least here, we're going to do the percentage of the fluorine, which is going to look a whole lot like the chlorine one we just did, except that I'll have 19 times 2 over the total of 120.91 times 100, and that gets a percentage of 31.43%. Now, to be honest, I could have figured out this fluorine a sneaky way. Obviously, the 3 percentages should tally to be really darn close to 100. I mean, it should be 100 on the nose, but sometimes with rounding and things, you might come out to 100.01 or 99.9. So theoretically, I could have gotten this last percentage by subtracting the other 2 from 100. I would caution you against doing that because I actually like to use the adding to 100 to make sure that I didn't mess anything up, so I use it as a double check. So that would be my kind of words of wisdom to you, is once you get these numbers, add them up, see if they come out really darn close to 100 or 100 on the nose, and then you can kind of see if maybe you did your problem correctly. All right, let's look at the next one. It says, what is the mass of 4.25 times 10 to the 24th molecules of CCl2F2? All right, so here I'm kind of trying to get between the mass and molecules. Now, it doesn't specify a unit to solve my mass in, so I actually get to pick here. I'll be honest, I usually pick grams unless there's a compelling reason not to, which we'll address one here in a little bit. So I'm going to solve this in grams. What is the mass? I'm looking of the CCl2F2, so I'm going to kind of write that here. Looking for the mass of the compound, and I have molecules of the compound. 4.25 times 10 to the 24th molecules of CCl2F2. Now, the reason why I write the compound in both places is just to remind myself that I'm not trying to get to an element inside of it. So I don't need any kind of extra special ratio to work back and forth. Now, I kind of already know that a good tie between molecules and mass is moles. So more than likely, I would want to take my molecules into moles, and then I could go moles to mass using my molar mass. But let's say you're kind of starting off and refreshing your memory on how to do this, and you get kind of stuck. A great place to start is that chart that I showed you on the previous page. Okay. This is kind of like a nice little guide map to say, hey, I'm at molecules right now, again, because this was a covalent compound instead of formula units for an ionic. And so I want to work between those molecules, and I want to get over here to grams in the molecules. So I can see I can go molecules to moles using Avogadro's, moles to mass using molar mass. So if you're kind of getting stuck and kind of trying to refresh your memory on how to do these problems, this is kind of a great place to start refreshing your memory. All right, so I'm going to go ahead and set up my dimensional analysis. Again, I like to use the parentheses, but if you like to use the T-chart, then help yourself, okay? I'm going to have molecules on top here, so on this step, I want to put molecules of CCl2F2 on the bottom, so that way those units cancel, and I'm going to do moles of CCl2F2 on top. And again, when you're doing molecules to moles, Avogadro's number tells us how many particles, how many molecules there are in 1 mole. Okay, so don't forget to put that one with moles when you're using Avogadro's number. We do the same thing when we're doing the molar mass step. Now, what we've done so far is we've ensured that the molecules and molecules unit have canceled out. So now that I have moles on top, I want to get that unit to cancel out eventually, because I want to end up in grams over here. So to get this unit to cancel, I need to put moles of CCl2F2 on the bottom, and I'm going to put my grams of CCl2F2 on top. Okay, so this is where now I can use my molar mass that I determined up here of 120.91 grams per mole. So again, that number needs to go with grams. 120.91 grams for every 1 mole of that substance. All right, and so now that I have this set up here, moles and moles cancel out unit-wise, leaving me with grams. That's what I was trying to get to. And I want to kind of refresh how to plug this into your calculator, because I know for some of y'all it's been a while, or you were just shown wrong from the get-go. So I want to make sure that we're plugging this in correctly. First off, do you plug in this number right here? I want to use the E key. Do not use times 10 carats. It's the worst thing you can possibly do, especially when you're doing dividing problems like this where the times 10 ends up in the denominator. Trying to do it with using the times 10 carat can really mess up your order of operations, so you got to be really careful. So I do 4.25, then I hit the second button, and then I hit EE, which is this, you see it right above the comma. So if you hit the second, that'll put E into your calculator. This E tells your calculator times 10 to the. And then all you have to do is enter in your exponent of 24. No times, no tens, no carats, none of that. This is all you need to enter into your calculator. So then the way I plug in the rest of this is I like to plug in exactly how it looks. I open a parentheses and I do 1 divided by 6.022, second E, 23rd, close that one off, open up the next one. 120.91 divided by 1, not that the divided by 1 does anything, but whatever. Close that off, and then I hit enter, and it calculates it for me. Woohoo. Now, here's where I want to address sig figs. My original number of 4.25, ignoring the times 10 to the 24th, has 3 significant figures. That means I want to show 3 significant figures in this answer. Cutting off my answer here does not change the magnitude of the number. So I'm going to report 853. Also, this 3 beyond the decimal does not round up the 3 in front of the decimal. So that digit beyond does not round up the digit before. So I'm just going to report 853. And then, of course, I want to put a unit with my answer. I was solving grams of CCl2F2. Okay, for the next one, it asks how many molecules of CCl2F2 are found in a 10 kilogram tank of Freon 12, the Freon 12 being the CCl2F2. So again, we're dealing with the same substance there. So again, I don't have to worry so much about converting back and forth between particles within. Okay, but I am going to go ahead and set this up. So I'm looking for how many molecules of this CCl2F2 in the 10 kilogram tank of, again, the CCl2F2. And again, if you get annoyed with writing CCl2F2 every time you could put CPD for compound, the good news here is that both of these are in terms of the compound. So nowhere do I have to switch between the compound and an element inside of it. So that's going to make our work a lot easier here. However, I do notice that this guy is in kilograms. And I know that when I'm working with molar masses, I'm typically in terms of grams. So the first thing that I'm going to do is do a kilogram to gram conversion. Now, since kilograms is on the top, I'm going to put my kilograms on the bottom. And I'm going to go to grams of the CCl2F2 on top. Now, I like to use the scientific notation equivalents, kilo being 10 to the third, milli 10 in the negative third, centi is -2, micro is -6, nano is -9. I like using those. And when we use those, remember that 1 always goes with the prefix. So 1 goes with kilo. And as I just mentioned, kilo is 1 times 10 to the third. Now, I know some of you know that there's 1,000 grams in a kilogram, so you could have used that as a conversion. This is showing the exact same thing, 1,000 grams in 1 kilogram. So take your pick on how you want to do that. All right, so now that this is in grams, now I can go grams to moles and moles to molecules, just like we did on the previous problem, just kind of in the backwards direction. So I'm going to have my 120.91 grams of the CCl2F2 down here to the 1 mole of CCl2F2. And then I'm going to have my 1 mole of CCl2F2 to 6.022 times 10 to the 23rd molecules of the CCl2F2. Now, on this one, we got to be really careful on sig figs. 10 with a decimal point only has 2 significant figures. By the way, if the decimal point wasn't there, it would actually just have 1 significant figure. So I only want to show 2 significant figures in this answer. This answer comes out to be 5.0 times 10 to the 25th molecules of CCl2F2. All right. Next one asks, what is the mass of chlorine in 5.56 milligrams of CCl2F2? So again, it doesn't specify a unit here, so I get to pick. However, I notice that there is a unit of mass already mentioned. So in order to kind of be consistent here, I'm going to actually use that same unit of measurement. So what I'm going to do is I'm going to solve this in terms of what is the mass in milligrams, just like this one was, of chlorine. Now, I will warn you here, we know that chlorine by itself is typically diatomic, and if I was writing a reaction, I would want to address that. But here, I don't want to address that because the chlorine is inside of a compound. I'm just addressing how much of that chlorine element is in that compound, not dealing with chlorine diatomic in nature. So kind of be careful there when you're doing these compound stoic problems. You don't really have to worry about the diatomic issue when you're doing particles within a compound. Okay, now if you're wondering, why did she pick milligrams? Well, there's kind of a sneaky reason I did here. I'll explain why, so I can do less work here. So CCl2F2, I'm going to put my starting substance there. So I can see that I'm trying to get back and forth between the mass of a compound to the mass of an element inside of it. Kind of like what we saw on that first page. Okay, those examples on the first page. So there's going to be more than one way you could solve this. You could take milligrams into grams, and then you could take grams into moles. You could set up a mole to mole ratio. then take moles back into grams, grams back into milligrams, and you get your answer. Does that work? Yeah. But I don't know if that sounded to you like a lot of steps, but it did to me. And so I don't want to have to do that many steps. You could do a percent composition. That would totally work. I'm personally going to do a mass ratio step. Anytime I'm trying to get from mass of a compound to the mass of an element inside, I know that mass ratio is a really good option. And if I remember correctly, up here, I kind of set up what that mass ratio might look like. Now, this mass ratio was in terms of grams, and I want my mass ratio this time in terms of milligrams. But here's the deal. If the mass ratio was true in grams, it's also true in milligrams. Okay? As long as I'm keeping the metric unit in constant, like I have both of them in kilograms or both of them in micrograms, this ratio will always hold true. That's the beauty of the metric system and being a base 10 kind of unit system. So even though this ratio was in grams, I can also set up this ratio in milligrams. Now I will warn you, sometimes you do have to flip-flop this ratio, like sometimes you need the element on the bottom and the compound on the top. But if I look at where my units are here, I notice that I have milligrams of the compound on the top here. So that means I want milligrams of the compound on bottom to cancel out. So I want to keep the compound, kind of crisscross here from each other so that way that unit cancels out. So that means I am going to have my element on top. And just like I set up back up here in this percent composition step, I'm going to have for every 35.45 times 2 milligrams of chlorine, that's going to be equivalent to 120.91 grams of the, milligrams. Here, let me cancel that out because I wrote it here, right? 120.91 milligrams of that whole entire compound. So again, even though that was a grams to grams ratio, it's also true as a milligrams to milligrams ratio. And that saves me from having to do any kind of metric conversion here. This does have 3 sig figs, so my answer here does end up being 3.26 milligrams of chlorine. All right, last but not least down here, it asks what number of fluorine atoms are present in 0.75 moles of CCl2F2. So I'm going to kind of start off here with asking myself, hey, I'm looking for the number of atoms of fluorine. I'm starting off with 0.75 moles of CCl2F2. So again, I see I'm going back and forth between the compound and an element inside of it. So that means I've got some options here. I could do a mole to mole ratio, and then I could do a moles back into atoms, or I could do a moles to molecules ratio, and then do molecules to atoms inside. I have options. I'm going to actually show you both options because I want to show you how the math ends up being the same no matter which way you're doing it, okay? So let me do it the way I mentioned first. I'm going to set up a mole to mole ratio. Now, when you do a mole to mole ratio, you say, hey, for every 1 mole of that whole compound, how many moles of the element are inside of it? Well, there are 2 fluorines inside of it. If I decomposed that compound, I could create 2 moles of fluorine. So that got me to moles of fluorine. So then to get to atoms of fluorine, I would just simply do 1 mole of fluorine for every 6.022 times 10 to the 23rd atoms of fluorine. A moles to particles ratio using Avogadro's. Does that work? Absolutely. However, I do have one other option that you could do, and it will get you the same place. What you could do instead is right here. I'm going to come down here. I could say, hey, for every 1 mole of CCl2F2, I'm going to take it to particles. For particles of CCl2F2, I would call them molecules. So I have 6.022 times 10 to the 23rd molecules of CCl2F2. Let's squeeze that in there. There we go. Okay. Now I could set up a molecules to atoms inside ratio. For every 1 molecule of CCl2, F2, for every one of the big piece, there are 2 atoms of fluorine inside of that one molecule. Now here's the deal. Look at the math I'm doing on this first method and the second method. Both methods, I'm going to take my 0.75, multiply it by 2, and multiply it by Avogadro's number. It gets you to the exact same place. So it's really a matter of take your pick on which way you like better. By the way, this has 2 sig figs, so I would want to show 2 sig figs in my answer. The answer here ends up being 9.0 times 10 to the 23rd atoms of fluorine. All right, hopefully you kind of have some of this coming back to you. This is one of those things that the more you practice with compound stoich, the better and just, I don't know, more familiar you get with it. So make sure you take the time to practice with these type of problems. If you have any questions or need any help, please feel free to email me. Bye, guys.